Hello. We're going to make a little video here that shows visual analysis of some dynamic light scattering DLS data. I have two purposes. One is to demonstrate kind of how we do this for fitting multiple exponentials using solver for that purpose. Maybe later we'll do one with a grid search as well, but that would be a separate video. The other purpose is to demonstrate for some collaborators who are looking into the artificial intelligence way to analyze data. And in that project we're sort of hoping that we can just look at these plots and say it's good or it's bad, it's been dusty or it's not dusty, whatever. So we're going to focus mostly on the correlation functions itself. What to do with the intensity data is pretty obvious if it has sudden spikes in it intensity as a function of time, and that's not a good thing. The data are imperfect. They come from polystyrene and toluene solutions. It's just garden variety polystyrene that we bought from Sigma Aldrich or somebody. I think the molecular weight is about 170,000, although I can't remember if that's in weight or number average molecular weight, but it doesn't matter. Our starting point here is just the file itself, and all I did to open this was to right click on the output of the correlator and say open in Excel, or open using Excel, or open with Excel. And you can see that it has correlation function data, and then at the bottom it has some count rate trace information. And it actually probably has, at the very bottom, cumulative parameters that you could use to estimate the decay rate, so it automatically does an analysis of that. There are 8 active correlation functions in these data sets. The first column here is the lag time, and then the next 8 columns over, these ones, are the correlation functions, and then you got some zeros over here because we have 8 detectors instead of the maximum of 12. Alright, so let's go back to what it would look like just when we opened it. Open with Excel. This is what you start with, and we'll mark the data off as correlation function. Actually, it turns out to be a little bit easier for me if we go right here and insert a line, a row, sorry, because then I can snap to the bottom and not hit the whole file. So it'll stop down there. So what I'm going to do, first thing to do is plot the data. So we'll go down across here, and then I'll do a Control Shift down, and then we've grabbed all the data. We go to Insert, we go to Scatter Plot, and there's a scatter plot. Ugly looking thing because of the linear time scales. So maybe the first thing to do is to decide how much of this we're even going to bother with. Okay, this actually is an exponential decay, rapidly coming down. Let's actually just try to trim it a little bit, and I think it'll be helpful for this purpose to click this axis and make this be a logarithmic axis. And that looks a little bit more like it probably did on the correlator instrument's display. And what I immediately see here is a bunch of numbers greater than 1. What we're being shown here is G2 of lag time t versus t. So that's, actually I should say versus log t. Okay, so that's what that is. And we know that for homodyne correlation functions that have Gaussian distribution of intensities, you can't exceed 1. And when it seems like you do exceed 1, that's some sort of instrumental problem. In this case, lots of correlated after pulsing in some of the detectors. So let's try to eliminate that let's close this little area over here. Don't need that right now. And we'll, I want to drag this plot. Let's just delete it. Control delete it. And we'll put it up about here, I guess. There's the plot. And I want to do, it's all selected, so what I'm going to do is scroll down to where none of these numbers is bigger than 1. Okay, and lose some of those early channels. So here's 1.3, 0.6. Actually, it dives down pretty quickly from 1. But I'm going to just snap it down to like about, there. Let's see what that looks like. Yeah, that looks better. Okay. So there may still be a little bit of correlated after pulsing going on, or this could actually be some real scattering contributions to the correlation function from scattering of smallish particles. I know from looking at this that since it never has a real clean plateau here, and then it has this sort of dive down zone there, I know right away that this is sort of a polydispersed system, bimodal perhaps, something like that. And we'll see that as we generate our other plots. Remember in the infamous tutorial review, chapter 12 that I always refer to, we talk about 4 plots, ln, log, ln, log, and log, ln, I guess. We'll generate those, but I want to trim this a little bit further first. Let's actually keep that for right now and copy it and make another version of it there. And in this version, let's try to get the ln log one. Format this axis to be, the y-axis should be logarithmic. Yes, it complains. And now I've got the log plot. Okay, great. I wanted that, so I should do log. Change this. And I guess I'll put a bracket there or something like that. Oh, these should have been -1, by the way. So I have to fix that over here too. There it is. So now I have the log plot. And I guess that could be kind of useful. We could sort of look at what's going on here. There's this rapid decay and then some really slow decay here, which may be due to dust or fluctuations or something. But I would assert that most of what we want is sort of terminating around here. This is, can't read the axis too well, 10 to the -1, 10 to the -3, 10 to the -4. That's got to be about the limit there. Well, with any luck, I can choose that, all of them at once, which apparently isn't going to happen. And so we'll have to do that manually until we get up to whatever time that is. This is a little hard to see on this scale. Well, let's just go by the y-axis. We'll say 10 to the -4. We'll just drag it up here. Certainly the negative numbers are not desirable. So we'll do this kind of the hard way, I'm afraid. Sometimes I can get it the easy way, sometimes I can't. So 10 to the -3 or so would be probably where these data are going to crap out on us, sort of in there. Let's see, was that a nice even number? It's 204. Let's go for 200. You know what? Let's go. Let's be a little more restricted. Let's go for 160. Okay, there's 160. So one of those got cut. I can't even tell you which one. I guess we'd have to select all of them and try to do that eventually. All right. So I think our range is going to be from about row 71 to about row where did it stop? 160. Okay, row 71 to row 160. So that's actually easier just to kill this plot and get that again. Okay, so from row 70. And row 160. And just plot that again. Back up here where the other plot is. I was thinking it might be easier just to do it. Okay, there we go. So when we do that selection, this is linear, you can see that it looks sort of like exponential decays with something very rapid happening at the very beginning and something much slower happening later on. And now we have what I think are going to be pretty good channel choices. Okay, so maybe this is the best one to just copy and use as our basis for making the 4 plots. So there's linear. Let's make this one semi-log, or log, what means logarithmic of this thing. Oh, come on. Format axis. Log it. Yes, we know. Aha! Okay. So that's our semi-log plot, which I very much like. I think that one is normally arranged over here somewhere, whereas this guy goes there. And then this is log of that. And let's take this one again as the, well, I guess it made more sense to take this one. And format the axis so that the x-axis is also log scale. So now we have, I would say, pretty reasonable selections. Maybe on this one here we would come on. Make this maximum maybe 0.25. That's nice. Okay, I think I like that. Kind of in a Bob Ross mood tonight. You can do anything you want with these axes. That's the beauty of it. You can just do whatever you want. But just looking at it, you see there's this rapid initial decay in the linear. And when you look at the log linear, you can see that sort of, and then it's straightened out, kind of. At no point do you get the impression that these things are really straight lines in any part of their region. For example, if I was to blow this up and go to the Insert menu here, and I think it's under Illustrations and Shapes, and here they do that. How would you draw a line through any of these? If these were monodispersed, how would you draw a line through any of them? It would not be easy. You could do from, this blue one, you do fine until you get up in that little zone right in there, and there's not much you can do to draw that line. And I think if we expand this scale a little bit more, it'll be even more obvious that that's the case. Let's expand the scale to, let's say, 0.15. Okay. And maybe we want to be a little more restrictive on this scale too. Let's see, a minimum of 10 to the minus fifth is ridiculous. Let's make it a minimum of 0.01. There we go. Now, how would you draw a straight line to it, any of it? Some of these some of these angles show a problem, like this one has a little lumpy thing there. That's a problem. That's actually due to some sort of ringing effect there in the system, maybe a vibration, maybe electrical oscillation at some pretty high frequency. But there's no way to draw a straight line. So we think that, a single exponential is not going to work. Or at least it's going to miss some of the channels. It might work at some of these, this part out here where the bigger, slower stuff is that is actually reasonably linear. I could probably do a decent line for some of it, Let's take this one here. Let's take this top one here. That's the top one, slowest decaying, must be the lowest angle. And, I could probably get a line to that, and that line would have a slope of gamma 2, if we're looking at since we're looking at the homodyne or second order correlation function, or twice gamma 1 would be that slope, and we could, evaluate that pretty easily, either graphically or actually using fitting algorithms, and you get an idea. You might make a little note on a piece of paper or something, what channels you get to use here, how far you get to go in the time, by the time we're at 10 to the minus 2, this is 10 to the minus 2 milliseconds. That's the ALV standard of time is milliseconds. You could, say, okay, I can analyze this slower part and get much of it, but a lot of the signal is in this initial decay. Pretty big amounts of the signal are in this initial decay. All right, so I think I can Control Z my way back to someplace I'd rather be here. There we are. And in the linear scale, you can say that you can see how big that rapid decay is more easily. Let's see if we think we start at like 0.7, the first 0.3 of it or so, down to 0.4, is the rapid stuff. So what is that? That's 3/7. 3/7 is whatever 3/7 is. 30% or so, I guess. Right. Looking at this, as I think I already mentioned, there's a lot of slopiness here. There's no real level plateau, so you know right away that this is a polydispersed sample. And this one has just been useful for us to try to find out what channels to keep. So what I'm going to do now is take these channels, sort of one by one, and put them in a different spreadsheet, set up a solver for analyzing it, and then we'll successively drop different channels in there. The lag time matrix stays the same at all times. Okay. So I'm going to come from here, and I said down to 160. New spreadsheet. I'm going to paste this as values. I apparently already had something here, which is kind of handy. We're going to do paste as values. It does something to that plot that I don't like, but who knows what it did to that plot. It's okay. I'm going to get rid of that plot anyway. So these are going to be our values, and this is, we're going to make a note from 70 to 160 channel row numbers. Now look, I've already set this up with some variables, A1, amplitude 1, 0.1. And you see it has a defined name there, ample 1. Amplitude 2 is called ample 2. Gamma 1 is called nothing. Actually, it's called gamma 1 with a 1m, gamma 1 and gamma 2. And it's good to give units for these things. These will be in hertz. Since I want those to be in hertz, I should probably convert all of these. It's going to be easier on me if I convert those to seconds instead of milliseconds. So what I'm going to do here is I'm going to say equals this divided by 1,000. So that's what that is in seconds. And it shows you O. What happened? Something bad happened. Oh, I just copied all this, totally wiped out my data. That was dumb. Let's try that again. From 70 to 160. So I totally screwed that up. Well, that happens. Let's paste those values again. I don't see why that would have caused the trouble. There we go. Let's insert this way. This should be lag time, milliseconds, give it a header. Lag time, seconds. So I'm going to put it to the left this time. So this is going to be equal to this divided by 1,000. Okay. And then let's see, let's make this be plotting that version of time rather than the one I have. There we go. Should be the same, essentially. This is left over from something I did earlier, I guess. Doesn't matter. I think this is left over from some earlier thing. Let's try there. There. That's like, I like that. Okay, so that's our plot. And now what we should do is we should calculate amplitude 1 and amplitude 2 that match that signal. And our equation here, I don't know if I have the ability to draw, maybe. Our equation here, what we're really looking at here, is G2 minus 1 is equal to A1 e to minus gamma 1 t plus A2 e to minus gamma 2 t, and that should be squared. And then there probably ought to be some other scaling amplitudes. I guess maybe we can just make that work. We'll just see how that works. I think that should work. I'm just going to adjust A1 and A2 until it does. All right, so that's the basic idea, the equation that we need. So let's build that. Let's let's see, we'll do G2 minus 1 calculated, okay, equals amplitude 1 star exp minus gamma 1. And the numbers that are in there now are just there for the hell of it. Plus amplitude 2 star exp minus gamma 2. And I forgot to multiply by a time, which was dumb. So I better do that now. And I better close that. And I better go fix that up here. And that could be A6. And then I think all that is supposed to be squared. Okay. And we propagate that down. I guess it's varying and behaving more or less. And we add it to the plot. Add a data series. Really? Have to click in the right place somewhere. Somewhere has to be right. Select a data, that's the one. Add calc series X values from here to there. No, okay. And series Y values from there to there. Hopefully that worked. And it's there. And since it's a calculated curve, we would like it to be a line. So we should format it to be a line. Format the data series to be this. Markers. Line. Marker. Marker options. No markers. Line. Solid line. Color, I was happy with it being some other color, but that's the color. Okay, so there's our fit. And then we would just start playing with some of these numbers here. And, well, I don't know, you can just sort of play with them. 0.5. 0.5. Okay, so that's too much, huh? And let's see, I need it to decay faster than 5,000 hertz, so let's make that let's make that 20,000 hertz, this one. It doesn't matter which one is 1 and which one is 2 as long as you kind of keep it in your head. You know what, that might be close enough for Solver to go ahead and do the rest. So what we should do now is we should get difference. Let's see. Diff square. Okay, we'll call that diff squared, so that's equal to that minus that squared. Now, why don't I call that SE? And then we're going to come over here, we'll call it sum squared error. Okay, so to get the sum squared error is going to be equal to sum of all this stuff. Okay. And then we need a solver now to come in here and fix this. Hopefully we can get it working. Design format. Home. Add-ins, data. That's under data, isn't it? Yes. Data analysis solver. So we're going to set our objective, the sum squared error, to be a minimum by changing these two. And it puts colons between F's maybe and these two. Let's see if that works. F2. I don't know if I can do that. Can I do it? Maybe I just have to type them in there. A1, A2, F1, F2. I bet it's not happy with that format, but maybe. We'll see if it works. And then you get some choices down here, and in principle you can study what they all do. GRG, nonlinear, we'll try that one, I think. There's some options you could choose. I don't usually start by playing around with those much, maybe later. Let's see, it seems like it understands. Now, A1, A2, F1, F2, gamma 1. Oh. Was one of these not named? Oh. That's not going to work. Okay, I want to do this right. This should have been D1, D2, D2, $3, $F, $3, 2, $F, $3, and it looks like it did it, and that's its solution. Okay. Now you could, if you wanted to do you could try a single exponential fit, but it would likely be even worse than this. I don't really think this is the best fit that you ever saw. For example, I don't know why it would set that to 0, but it somehow did. And it didn't seem to adjust these, so I wonder if this solver is working or not. Let's go again and see. Ample 1, ample 2, gamma 1, gamma 2, subject to the constraints. To add a constraint, we know that the gammas must be positive, right? There's no such thing as a negative scattering. Should be greater than 0. Okay. Let's see if that does any better. Maybe. Maybe not. Okay, looks like it's doing a little bit better, but these are still huge, humongous misses. Let's, while we try to sort that out, let's add something else that any of these really should have, which is the residuals plot, right? So we could do, that's going to be a plot of lag times. And the error, actually I don't have this, I don't actually have the error, I have the squared error. That's kind of too bad. So I guess I should probably go get that. Let's move. Let's just put that here. I guess it's kind of not where it should be. So that's going to be calc minus data. Should have put that in earlier. Okay, so we'll grab that. And we'll control and hope it'll let me grab this too. And look at that nasty looking residuals plot. Oh, come on. I don't know why there's this gap there. I don't know why there's a gap here. This should be on log scale though, to match the other one. Ah, looks better without that. Yeah, pretty much what we think. The residuals should be. We don't have a good model here for the size of the errors. Okay, so I think what I did is I went too far down here somewhere. I think I just dragged that too far down. Yep. I don't need any of this stuff here. This is all junk that was left over from earlier. You don't need any of it. Okay. There we go. So there's our ugly, ugly, ugly fit. And whether you can get it to be better than that or not depends. You see it's really hardly changing these gamma terms here. And I suspect that the problem is that it's dealing with numbers that are too small in the lag time. So what I might really want to do, I might improve my situation a lot, even though I would like these to be in seconds. Maybe I would be better off dealing with larger numbers that we have in the milliseconds column. I'll bet you that's the source of the problem. And you'd have to code these things yourself or do a grid search type of thing instead of a gradient search to find out. I think I'll push ahead and just see what that would look like. Let's just try that. Let's just move the x-axis to be, oh, come on. Move the x-axis to be that guy instead. And we'll do the same for the fit. Okay. And then our decay times all have to be something else, I guess. I don't know why that would work. Let's put in 0.25 again. Okay. And 1,000 hertz in milliseconds. These should be millihertz. What would we call that? What would we call it? It's not a millihertz, it's a kilohertz, I guess. But I think our calculation is still based on the time, so it's okay. Actually, I think it's okay to leave it that way. times A6. I think I really want to calculate on B. I think everything else here should kind of hang together okay now. I think so. And I do think these are kilohertz. Then we will put kilohertz there. We'll put in 10, and we'll put in 500. There we go. Shall we see if it does better? Let's see. Can't hurt to look. Yep. So what have we learned? We've learned that Excel is really sensitive and doesn't do well with the numbers at the low end of the range. And the fit is doing okay. You see this little shallow depression down here. That corresponds to the issue there with this lump that we have, which is an electrical problem or a mechanical problem. But otherwise, it's pretty much nailing that baby. With 2 exponentials only, that would suggest, if we believe that the distribution of this polymer is bimodal. But we shouldn't believe this. Okay, so this is my decay rate gamma, and these are my amplitudes as a function of gamma. This is this kind of fit. This is the fit we're doing. And we know from the synthesis of this guy, which is undoubtedly some sort of free radical polymerization, that it might be possible for it to be something like that. Right? But there's no way it's exactly 2 exponentials, and yet 2 exponentials fits the data pretty well. Interesting, huh? So when you try these more generalized Laplace inversion methods that are discussed in Chapter 12, the light scattering tutorial review, what you'll see is that they have ways to give you something that looks like a continuous distribution, but right now you have no real excuse for using them because you can fit it perfectly well with 2 exponentials. So those distributions are a way of drawing what it thinks is the best possible answer. Now, we could, if we wanted to, see how well this would fit a single exponential. Okay, and so that would be a matter of going here. I'm going to save this text so that I can put it back later when I want it. I'm just going to put that text right in there as a thing. Okay, for that column Q, whatever. I'm going to take the text here. I don't think I really did it. I'm going to put it in Q1. I'm going to put a thing there. I'm not going to say equals Q1, for heaven's sakes. There, that's what I want to put. Did that work? No. Why can't I do that? Why can't I grab the text? Because I took the equal sign with it, that's why. There. Now I still should have this calculation here, and it should be fine. And what I'm going to do is just take out this term here. Bet there's an easier way to do this. What I want to do is okay. So now that's what a single exponential fit looks like. And we'll go to our solver. just let it do A1 and gamma 1. And I guess those constraints can still be 0. Since they're not even involved, let's see what happens. So that's our best single exponential fit. And you see it's hideous. Okay, it's definitely not as good as before. Well, I don't know how much of this I can control Z back out of. Let's just see. No, not much. I was afraid of that. So anyway, we'll go back to here. Get this text. Put it in the calculation where I had it before. Get rid of that little apostrophe. Let it run the solver again to put it back to how it was. And it's back. Always you should change these numbers around a little bit. Let's try 0.9 and 0.6. This is going to be absurd. Okay. And let's change this number to 10 and 50 and let it see if it can find the minimum from there. We shall find out. Yep. However, it's not the same answers quite as it was before. So you're finding that this is a little bit sensitive to the starting guesses. And that would improve if we had quieter data. And what it's telling us is that a number of different solutions can be found that seem to fit the data to within the noise. Let's try it. I want one that comes at it from below. And one that is like insane, 100 kilohertz and 1 kilohertz. What's that like? Quite different. Actually, this is a little bit like the first search, only A2 and A1 inverted. So the fast one is now what used to be the slow one. So that can happen, and you have to be able to ferret that out yourself. Let's feed it these very things again and see if it's even really converged at all. Maybe just running it again helps. Yeah, it did. And we're getting back to kind of where we were, except that now slow is fast and fast is slow. All right, so you've learned a little bit. I wonder if we ran it one more time, if it would behave. And you'll see that in other packages, like the origin package, you have the option to continue iterating. And so it basically has. Let's give it something ridiculous again. Okay, and let it go. That's kind of where we were. It came back. We'll let it do one more pass at it. See, it's 22.2471. And it hasn't changed very much. Maybe these changed a smidge. Okay, so that's basically what I wanted to show about how to set that up. And you would know if you tried a single exponential fit that it isn't working, and you would set a double exponential fit. And if you wanted to see what a triple exponential fit is, I think you'd find that you do not dramatically make any improvements that you could rely on in this case. So that's that. Thank you. Well, now I realize that I didn't actually complete the entire problem, and I don't really know that I need to, but I do just want to show what would happen next. I would go back to here and choose the next column. Okay, so I chose the first column. And remember, they're associated with angles according to what you see up here. So that was the 117 degree angle, one of our higher plots. Let's try one at the opposite end of the spectrum, this one down here at 50. That's the second from the last one. It's a historical accident that these are not in order, and I don't know what to say about that except that fixing it seems kind of like an ugly problem to us. All right, so that'll be the second to the last one. We'll use that one and see how that one comes out. So we're going to get the lag time data from we said from 70 to 160. Okay, and there's really no reason why it would be the same for all different angles except as a sort of a convenience. It really isn't. But if we're doing things right, that shouldn't matter too much. It's not exactly optimized. There's a lot of things you could optimize here. And we want the second to the last one, so I'll hit a control there and take up to the same level to 70. And that. I don't know what happens if I paste those into here directly. Might make a mess. Let's see what happens. No, it seems like it worked okay. It put them where I wanted it to. Not surprisingly, we went to a lower angle, so the experimental data shifted to the right to longer times. Longer times mean longer distances means lower angles, so that all hangs together. I bet we don't have to change hardly anything else for this thing to work. We would want to write down these numbers here, that we have. I guess we can put all that into another spreadsheet if we want. And we said that was 117 degrees. And you can calculate what the Q is for that later. And I think we said this one was, what did we say this one was? 54 degrees? Is that our lowest angle? $50 degrees. So we'll have that to work with later. Okay, so let's go here, we'll go there, and I bet we can just run it with these initial guesses, probably close enough. Go into Solver. Yeah, could be worse. Not surprisingly, the low angle data are better. And the reason is that you have more photons per coherence area per correlation time, at long correlation times. So that makes sense to me anyway. And residual spot looks better because there's none of that ringing going on. And that's probably because this is a better detector. To be on the safe side, we might want to run that again. Looking for changes. If there were changes, they were minor. We would want to do the same things here that we did before. Just randomly pick numbers and see if it finds it. More or less. And so again, I think it might be that it went to giving A1 be the, right now it's the slow one. It might have been the fast one earlier, but you have to sort that out yourself. The program doesn't really have any way to distinguish that. I suppose we could, if we wanted to, include that as a solver condition. We might be able to add a constraint, gamma 2 greater than gamma 1, and then, force that. I just don't do that. And so then you would drop these data in over here. And at the end of the day, you're going to assemble a plot, which I'm at least reasonably certain is going to look semi-respectable, of gamma versus q squared, where the fast ones do that and the slow ones do. I guess we should have 8 of these. Let's make it 8. I don't know if that's 8, but there should be 8 of both. And oops, this one here, the gamma, that slope will be 1 diffusion coefficient, and that slope there will be the other diffusion coefficient. So I think that should work, and we'll let you experiment with it and try. And if it doesn't, it's almost certainly because the data, particularly at the higher angles, might be kind of goofy.